news tweets, if you follow news accounts on Twitter, all those news tweets that might be happening in your timeline. Those tweets are more like events, little discrete descriptions of things that have happened, rather than that summary that you'll see in a broadsheet newspaper, which is going to cause us to want a new kind of data infrastructure. We're going to want a platform to help us manage this, not merely a file system to put things, not just somewhere we can store events, but really there are a lot of needs that grow up around that central storage that really comprise an entire platform. And that platform will unfold as this introduction proceeds. We need to be able to deal with these in real time. So our new computational tools that we build around that new data infrastructure are going to be focused on real-time processing. Also, we're going to take this view that we want to store events for potentially a long time, maybe forever, or as long as regulatory considerations will allow us. That idea that we're going to take events, store them in a log, is going to become the new organizing principle of this data infrastructure with all of these other components built up around it. And lest I bury the lead, it is Apache Kafka that has become the de facto standard for real-time event streaming. It provides all these things, right? At its foundation, it's a distributed log. So we can gather events from the outside world, store them in that log, and they're stored in a scalable and replicated and fault-tolerant way. We also have the need to integrate those logs with other systems. Not everything is an application built on top of Apache Kafka. And if you look at the things on this slide, there are these other systems in the world that need to talk to Kafka. Finally, when your data is stored as a stream of events, the way you run computations over that data is going to look different. We're used to this idea of, let me execute a database query, get a result set back, do some things to it. Now it's going to look different. We're going to write stream processors that transform events one at a time. And if we want to aggregate events and create some kind of snapshot of state, we'll write stream processors that do that kind of thing too. And it's not just me saying this. Many of the largest companies in the world with some of the most complex and daunting information processing requirements, and in some cases, the longest history of legacy systems stretching back decades. These are all people who are on this same event-driven journey. You see some of the logos here on this page, and really you'll see a mix of traditional companies, airlines, banks, some of these companies who have been using computers for as long as anybody has been using computers commercially, and also some newer companies, some of the first generation of classical internet companies like LinkedIn and Netflix, and even some more recent entrants like Uber and Lyft. These are all companies who are heavy users of Kafka and event-driven architectures. And it's 35% of the Fortune 500, as of the time of this recording, use Kafka for mission-critical applications. So that's not just a group of forward-looking developers in a skunkworks playing with open source somewhere and doing some cool thing. This is real line of business applications that are carrying critical customer data, executive sponsorship, budget, visibility across the company. These are very much real applications of Kafka. And let me give you an idea of some of those use cases. Now, I carry a credit card that has a logo on it that you saw on that slide a few slides ago. It's a financial services company. They issue credit cards. And I tell you, their real-time fraud detection is something else. And it actually does use Kafka to get that done. And it really is real time. This used to be a thing that they would find out the next day. Oops, we had fraud. And now I get a text message or a notification from the application within seconds when there's a transaction that they think might be fraudulent. And even occasionally one that is. I'll get a notification and I'm sitting at home on my couch not using my credit card. So this is a good thing. Automotive. Now, cars are increasingly Internet of Things devices, right? High-end cars these days, again, as of the time of this recording, will typically have a 4G radio in them and connectivity to a data network and the many computers that are in that car. Yes, folks, your car is itself a distributed system and it still works. Those computers have a lot of data that they're acquiring and things to report. And so often there'll be telemetry going back to a central headquarters and even sometimes bidirectional communication to enable services that the car provides that actually make driving a more pleasant experience. But all of that is fundamentally evented data, and that stuff is typically built on top of an event streaming platform like Apache Kafka. Real-time e-commerce. Now, what's the story here? Of course, commerce is also full of events. There are people clicking on websites, searching for things, putting things in carts. Those are all events, and you want real-time analysis of that to know how products are performing. You want a real-time, comprehensive view of each customer, and that kind of thing is hard to do with traditional databases. Of course, it's doable. You can build anything with just about anything, but the problem lends itself to an event streaming platform much easier, and people are finding that they're able to build systems like that with less engineering effort. And if you're the one building the system, that means you get to deliver cool functionality faster with less pain to get that stuff built. And that's huge. Customer 360 in general, even outside the world of e-commerce. I'll just stop and ask you, if you're a part of a large company, how many customer databases are there in your organization? Maybe you don't even know. Maybe you don't know. Maybe you do know. And the answer is like 6 or 7. There are these different lines of business that all have different views of the customer and different applications and different databases that are stood up around managing customers in some way. And they all have different views of things. If the business wants a single integrated view of that customer, of course, this is a thing people have been talking about for a long time with like master data management and things like that. But we're finding that event streaming provides some very interesting solutions to this problem. And by the end of this course, you'll see how some of those pieces fit together and how that kind of thing might work. Banking. Now, maybe you're thinking, I wired money to somebody recently and it took 2.5 days to clear. You're not going to tell me that's event-driven. Certainly, banking is one of those industries that has legacy systems stretching back to the beginning of commercial computing. So there's a tremendous tradition of batch processing and antiquated data communication protocols. But this is changing. Some of the largest banks in the world are deploying Kafka at the core for payment processing. You'd be surprised how much of this is happening. And there are some really exciting standards being developed so that it takes 2 days to transfer money in a bank situation. That's a little embarrassing these days. Pretty soon that may not be true, and systems like Kafka will be at the center of that. Healthcare. A modern hospital is increasingly bristling with IoT devices. There are lots of medical devices that are connected to a network and are reporting back. There have been some really, really cool Kafka use cases. For example, there was a hospital in Georgia that used Kafka and Confluent KSQL to process data from pediatric intracranial pressure monitors. A really, really neat use case. All Kafka based because there are all these devices generating events and sending them somewhere to be processed and understood. And by processed and understood, I mean, we want to create information that helps healthcare professionals take better care of patients and lead to better health outcomes. And that's a real thing that's happening. Online gaming is another fundamentally event-driven thing. If you think about every player who's doing anything, they're moving a control, tapping on a screen, hitting WASD, whatever it is that they're doing to play the game, those are all events. And other in-game things, it could be in-game AIs that are moving around and moving within proximity of a player. That's an event. All these things are events. And regardless of how the core game engine works, you need intelligence around those events. Whether you're just trying to do things like optimize in-game purchases by figuring out who's doing what right now, or it is a part of the application that drives the core game. A lot of this stuff in online gaming is fundamentally event-driven, and you have potentially very large numbers of events if it's a game that achieves runaway success. So this is another key use case for Kafka. Government. There are many, many public sector use cases for Kafka. That's not just the traditional 3-letter agencies that are processing events for the sake of national security or law enforcement, but really anything in government. A lot of the same things that drive Kafka adoption in the private sector, like migration to microservices, those same drivers exist in the public sector. Financial services broadly, as distinct from banking proper, again, tremendous drive to be real time and event driven here. People are expecting to interact with financial services on mobile devices. And whether you know it or not, you expect your mobile device to be a thing that responds to you right away, and a thing that in your pocket vibrates and tells you, oh, there's a thing that has happened in the world that I need to respond to. None of that kind of thing happens in batch mode. Those are all events that need to be processed right away. Kafka lies at the core of a lot of the businesses that are providing financial services that are doing that real-time migration, which these days is really pretty much all of them. So that gives you an idea what people are doing with Apache Kafka and what kinds of things different industries are doing with it. Hey, Tim Berglund with Confluent. This is the fundamentals of Apache Kafka within the course called Fundamentals of Apache Kafka. So we're really going to get into the fundamentals here. In this module, you're going to develop a mental model of what Kafka is. When we're done, you should be able to identify the key elements of a Kafka cluster and have some idea of what the basic responsibilities of each element are, explain what a topic is, and how it's composed of partitions and what segments are, and that basic sort of storage model of Kafka. Topics are what you're going to spend a lot of time thinking about when you're actually building applications on Kafka, so we want that to be pretty solid by the time we're done. Now, it is a fact of the world that lots of things happen in it. There are many events produced, and no matter what sort of industry you're in, like the industries you see pictured here, all of those things are producing events all the time. And Kafka's job is to manage and process those events. So to get data into a Kafka cluster, we have a thing called a producer. A producer is an application that you write. So that Kafka box there, that's either a Kafka cluster that you're operating, or maybe it's a Kafka cluster in a cloud service where you don't know too much about the operational details, but you know the service is there and it's reliable and you know how to connect to it. That Kafka cluster is that thing out there. Your job is to write programs that put data into it and read data out of it and do useful things with them. So all of those sources of events, we see connected cars, financial transactions, things happening in hospitals, boxes being shipped around the world. All of those are potential sources of events, and some producing application is aware of those events and takes an action to write those events into a Kafka cluster. And after they get written, the Kafka cluster says, okay, got it, sends an acknowledgement, and the producer moves on. Now, what's in a Kafka cluster? Let's break that down a little bit. It's made up of things called brokers. Now, if you will, just kind of set the Wayback Machine for maybe 10 or 15 years ago, when computers were things that you saw and they were in a data center, and you could like maybe go to that data center and it was this metal box with blinky lights and fans and that sort of thing. If you could imagine that helps make this a little crisper here. Those individual servers, those are kind of what brokers are. There's a Kafka process running on each one. Each one has its own disks. That's important. Every broker has its own local storage. Those brokers are networked together and they act together as a single Kafka cluster. When producers produce, they write into those things that are brokers. Now, if you're using Kafka in the cloud, you're hopefully not going to be thinking about brokers too much if you're using a fully managed service. There are brokers that are out there. You know that's true. They've got their own local storage. They've got some retention time set on the data that they're storing. That's maybe 5 minutes or maybe a month or maybe 100 years. They got some amount of time they're going to keep those events around. But in the cloud, of course, we don't think too closely about brokers. Those are a thing that's abstracted away from us. But it's true, and you should know this. Every Kafka cluster is composed of these things called brokers. And we never quite know how to refer to those. Are they machines? Are they servers? These are all sort of old words. They might be containers, they might be VMs somewhere, and I'll skip that for the rest of this course. I'll probably just call them machines or servers or some kind of legacy term like that, in as much as we're talking about brokers, just so you kind of have an idea what I mean. Now, that data gets written into that cluster. It's stored on those disks inside those brokers, and of course, we want to read it out. We do that with a consumer, and this consumer is a program you write. That Kafka cluster, those brokers, that's infrastructure. Somebody manages that infrastructure, operates that cluster. Ideally, it's a managed service in the cloud, but what you write is the producer and the consumer. You put data in and you read data out. And it's reading data that, frankly, usually gets pretty interesting. This is where a lot of the work happens on the consume side. What the consumer does with that data, well, that's up to the application itself. Is it generating a report, feeding a dashboard? Is there some other process that it's sending that process data to? Often a consumer will also be a producer and put its results into a different place in Kafka, that transformed data. But these are the fundamental parts of Kafka. You have a producer, you have the cluster itself, you have a consumer. And that model, those three pieces, everything that ever gets built with Kafka conforms to that model. Maybe you won't see the consumer and the producer directly if you're using something like Kafka Streams or KSQLDB, which we'll cover in a later module. You don't think about producing and consuming, but they're always there. These are the fundamental components of Kafka. So let's look at that again and add a component. We've got our producers there on the left, that Kafka cluster in the middle. Those producing applications are writing into the cluster. Then you've got the consumers. They're reading from the cluster. What's that thing on top? Well, that's a Zookeeper ensemble. As of the time of this recording, Kafka uses Zookeeper to manage consensus on a few pieces of distributed state. There are a few things that all of those brokers need to agree on. They need to have some consensus story on what is true, and Zookeeper is good at doing that. Now, again, as I said, at the time of this recording, there's an initiative underway called KIP 500. That's Kafka Improvement Proposal 500. That itself has spawned a number of child KIPs and a whole bunch of work to remove Zookeeper from Kafka completely. So at some point after this recording, that will not be there anymore. So it may be that you look at Kafka and the current release you're using, and maybe you see this video and say, well, there's no Zookeeper there. And that means a new day has dawned. So there's a lot of work to get that done. And that work is ongoing. But for now, Zookeeper is doing a great job being a distributed consensus manager for the cluster. Producers and consumers are decoupled from one another. So a consumer doesn't know anything about the producer that produced the data that it's reading. Likewise, when you produce data, you're not sending it to a particular destination. You're sending it to a structure inside the Kafka cluster. That's called a topic. You're producing that data to a topic. We'll cover those more in a moment. But you don't know anything about who's consuming from that topic. And that decoupling is intentional. That means that there's a whole category of state information between producer and consumer that is simply never managed. Producers write data in, consumers read data out. That also means that producers can scale. I can add producers that write data into a cluster without the consumers knowing. I can add consumers that are reading a kind of data that has long existed. Maybe I've got this long history of records of sales transactions in my cluster. I add some new fraud detection algorithm. Well, that's a new consumer. None of my producers need to know. They can fail independently. They can evolve independently. They're decoupled, so they don't need to know about each other. Revisiting Zookeeper for a moment, what does it really do? Well, authorization information, that's access control lists, those are stored in Zookeeper. The management of failure. So when a broker fails, there are going to be various pieces of a topic that broker is the leader for. They're replicated in other places in the cluster, but the way that replication is organized and who's in charge of each replica and that sort of thing, that is managed by Zookeeper. So when a broker dies and the cluster has to decide who gets responsibility for the data it was managing, Zookeeper participates in the election of new leaders for those things. So that's basically what it does. Little bits of metadata, failover, leader election, access control lists. That stuff is all currently in Zookeeper. I've used this word a few times, topics. Now I want to really give you a definition of what a topic is. A topic is a collection of related messages or related events. You can think of a topic as a log, as a sequence of events. Now, there are some exceptions to that. I'm going to unfold some concepts here that help you manage those exceptions. But for right now, just think of it as a sequence of events. A topic is this list of things. And when a producer writes a new one, it just puts it on the end, and the previous ones are kept. I can have any number of producers writing to a topic. I can have a producer writing to multiple topics. Likewise, many consumers can consume from a topic. All of those relationships are end-to-end. There isn't a theoretical limit on the number of topics. There's a practical limit on the number of what are called partitions. We'll get to partitions in a moment. But topics by themselves, it's not like you can only have 50 and then you need to add nodes or anything like that. You can really have conceptually as many as you'd like. And I did say partition, didn't I? So I better tell you what that means. Now, here's a cluster over on the left. It's got a number of topics in it. Let's zoom in on topic C. Now, that topic is a log, and it's a durable log. It's persistent, which means what? It's going to be stored on disk somewhere. And the broker that partition lives on, well, that's just a computer at the end of the day. And if you're writing messages into that topic and reading messages from that topic, that's work. I/O and computational work that computer has to do. None of these things scales forever. You can't have storage scaling forever, and you can't have that pub sub activity on that broker scaling forever. So you might want to break your topic up into pieces. We call those pieces partitions, and then be able to allocate those partitions to different brokers in the cluster. This is key to how Kafka scales. I can take a topic, partition it, and allocate each partition to a separate broker. So when I said a topic was a log, and I kind of put a little asterisk on that, and there's an exception to really what that means. Formally speaking, a partition is a log. So every partition has strict ordering. When I produce to a partition, I put the message on the end of the partition. That's the only place I can put it because it's a log. I can't disturb any of the previous messages. They're all immutable events. I just put things on the end. And so that is a log, and the events in that log, that partition, are strictly ordered. A topic having been broken into partitions, you may not have strict ordering over all of the events in the topic, so you've always got ordering within a partition. And if you want to look at an implementation detail, really drill down into what a partition is, on an individual broker, that log file is going to be represented by multiple log segments. Those are individual files on disk on that broker, and it's really a set of a few files. There's some indexes and things like that. So that segment is a thing that exists on disk on the Kafka broker, and each partition can be broken up into multiple segments. Usually, unless you're deeply involved in hands-on administration of a Kafka cluster, you're not going to think about segments so much. But you do have to think about partitioning as you think about how to model data in topics. It's very important. Let's look at that again in color. If you can see those colors, topic A is green, topic B is, that's kind of a mustardy orange, and I want to call C sort of a cornflower blue. And you're welcome to correct me in the comments if you think any of those color names are wrong. But this cluster now has 4 brokers. We're calling them 101, 102, 103, 104. And you can see how the partitions of each topic are broken up. So topic A has partition 0, 1, and 2. You see partition 0 is on broker 101, partition 1 is on partition 102, partition 2 is on broker 104, and none of topic A is on broker 103. I won't go through all of those, but you can kind of pause the video if you'd like and look through that diagram and see how those partitions are distributed. The cluster does that automatically when a topic is created, by the way. It makes decisions about where those partitions are going to live. What a Kafka cluster doesn't do is keep track of the size of those partitions and move them around if one broker gets overloaded as topics get created and destroyed. Loading, of course, does not stay constant. So this is functionality you'd have to add yourself to keep those things balanced. There are parts of Confluent Platform that will help you do that, make that automatic. And of course, if you're using a managed Kafka service, this sort of thing is a thing that you know vaguely. There is a team of highly skilled software developers and site reliability engineers who are making sure this kind of stuff works for you, and you don't have to worry about it. You see over there on the right there, the log files. Each partition, again, is broken up into individual segments on disk on the broker as a really drill down implementation detail into what's going on the broker. Let me just refresh exactly what I mean by a log. This is important. You probably know this, right? You've probably written to a log file at some point, or at least read one. And you kind of know instinctively, even if you never thought about it, the semantics of a log. So when you write something to a log file, where does it go? It goes on the end. It has to go on the end. It doesn't go at the beginning. That's already happened. That sequence of things has already happened. You can only add new things to the log because the rest is a representation of what has happened in time up till now. Also, all of those ordered entries prior to now, those are immutable. If you're editing one of those or deleting one of them, there's almost something like ethically suspect about editing a log. Like, what are you trying to hide? You know, you conspiring in a crime or something? So logs are immutable records of things. And the semantics are when you want to write to a log, you put it on the end, and that's it. And those are immutable after that. You may choose to expire things past a certain age, and that's certainly the case in Kafka. You can set a retention period on a topic. But this is what a log is. This is this fundamental data structure that Kafka is based on. And those numbers you see there, the 0, 1, 2, 3, 4, like that, those are real in Kafka. They actually start at 0, and they just monotonically increase like that forever. And there are many, many bits of them, so you're not going to run out. But every partition has its own unique offset space. So that's a real thing. You can actually find that out when you produce a message, when you consume a message. The API, you can poke into things and it'll tell you, oh, this ended up being offset such and such, or this was offset such and such. You usually don't need to know, but it's a real thing and it's there inside of each partition. An important fact about consumers, those blue boxes on the bottom that are apparently reading messages, consuming doesn't consume. It doesn't destroy the message. It just reads it. So you can have multiple consumers on one log or one topic in Kafka, and they can be at their own independent offsets. Now, of course, you'd like them all to be caught up, right? Everybody wants to be kind of close to the events that are being produced. So this processing can be called real time, but they don't need to be. In terms of the way the system works, one can start at the beginning and take days to catch up if you need to do that. They're independent consumers that are working from independent offsets. Later on, you'll hear me refer to this as a stream, this log or topic. I'll say stream. And these things in the stream are events. And the current time is where I'm producing right now. That's the present. And the stream extends back into the past. So different word means exactly the same thing. What's the structure of a Kafka message? Well, the things that you are going to think about the most are the key and the value. That's your Kafka data model. Every event is a key value pair. Now, very likely, there's going to be some structure in the value, right? That's probably some sort of domain object that you're going to serialize somehow and store there. There may be structure in the key. Often the key is a string or integer or something like that. But sometimes people have compound and complex domain objects that they serialize and use as the key. That's completely allowed. Every message has a timestamp. If you don't have a timestamp, one will be provided for you. So you'll get the wall clock time at the time that you produce the message. That's if you don't really care too much about the time. But if in your value in that domain object, if it knows the time it took place, well, then in the API, when you're producing, you can say, hey, the actual time is this. I don't care what time it is right now. This is the time of the message. You can set that explicitly. You also have an optional set of headers. Think of them like HTTP headers, which are themselves kind of string key value pairs. So you don't want to use this as additional payload, but this really is metadata. So these are properties of the data that you're going to be able to see on read. So consumers have access to these and can make decisions based on them. But that's it. You have key, value, timestamp, and headers. Let's dive into brokers a little bit. I've introduced them, but I want to go over their key responsibilities. Their basic function is to manage partitions. Now, as a developer using Kafka, you're thinking about topics all the time. You're creating a topic. You're thinking about the schema of a topic. What kind of messages does it have? What's its retention period? What are its compaction properties? All these great things that you'll learn about topics as you move forward. If you're a broker, you know what a topic is, but really you've got partitions. You're managing some set of partitions locally. That's what a broker does. It manages those log files. It takes inputs from producers, updates those partitions, takes requests from consumers, and writes them out. That's what a broker does. It does storage and pub sub. So those partitions are stored locally on the broker's disk, and there can be many of them, many partitions on each individual broker. So you see this core architecture diagram. Again, you've got producers. Those are applications that are writing to the cluster, brokers that are taking those writes and managing their partitions, and consumers that are reading from those partitions. The way consumers read from partitions actually gets pretty interesting. We'll take a look at that later. It would be a bummer if each partition only existed on one broker, such that if that broker died, the partition would die. You would not want that to be the case. And of course, Kafka does replicate. Each partition has a configurable number of replicas. 3 is typical. That's called the replication factor. One of those replicas is called the leader, and the others are called the follower. So when I produce to a partition, I'm actually producing to the leader. The producer is connecting to the broker that has the lead partition there. And it's the job of the brokers with follower partitions to reach out to those leaders and kind of scrape the new messages that they've got and keep up to date with them as quickly as possible. So, and that all happens in a very timely fashion inside a not properly operating Kafka cluster. It's not like they take seconds for that replication to take place. But there is a leader-follower distinction here, which makes consistency a lot easier to think about. Thinking a little more about producers, which you know now are these client applications, you might be asking, what language can I write those in? Well, Java is always the native language of Apache Kafka. The language library that ships with Kafka is a Java library. Now, the other adjacent languages of the JVM, like Kotlin and Clojure and Groovy and even Scala, there are always wrappers for those that make the Java library look idiomatic in those languages. But there are other supported languages as well. C, C++, Python, Go, .NET. Those libraries are supported by Confluent Platform. So if you need like a proper supported version of one of those, you can get that. Those are all based on a C language library called librd Kafka. That's an open source library that duplicates a lot of the functionality of the Java library, and many other non-JVM language libraries draw on that for their Kafka support. There are many more than that supported by the Kafka community. If you're wondering where Node support is and where's Ruby and all, well, believe me, they are there. In fact, there are often multiple choices for each one of them. There's also a REST proxy that we'll cover in another module that lets you access Kafka if somehow you're using a language that doesn't have library support, or if you just don't want to use that native language support, you can use the REST proxy. And of course, there's a command line producer tool as well. That's good for tests and scripts and sending kind of small amounts of string data into topics. Now, I said when a producer writes to a topic, it's actually writing to a partition, and these partitions are stored on separate brokers. And so how does a producer know which partition to write a message to? There are a couple answers to that. Now, if the message has no key, the producer will just have a round robin method that it applies. And it'll say partition 0, partition 1, partition 2, partition 3. And there are some exceptions and interesting ways to configure that, but that's basically what's going to happen. You're going to load balance in a round robin way. Partitions always stay even in that case, but you don't have a lot of ordering there. Now, if the order of events is important to you, you have the opportunity to order them by key. So if there is a key, then what the producer is going to do is hash that key, mod the number of partitions, that gives you the partition number it's going to write it to. So the same key is always going to get written to the same partition as long as the number of partitions is held constant in the topic, which probably should be in most cases. So messages with the same key land in the same partition, which means they are strictly ordered all the time. And that's an important thing because you might have a key, say you've got an Internet of Things application. You've got smart thermostats all over the planet, tens of millions of them, and they're all phoning home with temperature and humidity and every other kind of metadata every minute. And you want those to be ordered. You want to be able to process those in order. Well, if you make the key the device ID, well, then each device's messages are going to show up in order in a partition. So messages of the same key always land in order. It's possible to override all this and write a custom partitioner if you'd like to. It doesn't end up happening very often, but it absolutely is available to you if you need it. Consumers, again, are the programs that you write that are reading from topics. All the same language options as producers. And what they do is they poll. They actually will go out, that consumer program will go and ask the Kafka cluster. It'll say, hey, I am subscribed to this one topic, and this is the last offset I read. Remember those numeric offsets? Do you have any messages after that offset? And if the answer is no, then it returns, and the consumer can come back and ask a very short period of time later. Usually, of course, the answer is yes, and here are more messages, and it gets the messages and moves on. That consumer offset, the consumer is storing that in memory. That's state, right? We don't want that only to be in memory. So the offset of each consumer into each partition that consumer is responsible for is stored in a special topic inside the Kafka cluster, named, mysteriously enough, consumer offsets. So if you see that consumer offset topic, that's what it's doing. That's helping your consumers remember where they are. So if they go away and come back, the cluster can help them remember where they need to pick up again. And just like the producer, there is a command line tool to read from a cluster, which can be great for quick visibility into things and scripting and so forth. Usually not a lot of production code gets written with the CLI tools, but they do come in quite handy. As I've said, each topic can have multiple consumers. And by multiple consumers, I mean multiple different applications that are reading that same data. So they're separate code bases, separate images, separate builds, separate deployments, could be managed by separate teams. Maybe the people don't even know each other. As long as they've got the right to access the data, they can deploy consumers against that topic. Consumers also live in groups. Now that one on the top doesn't look like a group, that's kind of the degenerate group of one, but every consumer is a consumer group in Kafka, meaning I can add additional instances of a consumer. Like you see at the bottom, there are 3 instances of that consuming application. So imagine that's an Uber jar and you've built a Docker image around it, and Kubernetes is now deploying 3 of it instead of only 1 of it. That's a way that you scale out consumers. We'll talk about the details of that a little bit more in a future module. Let's come back to the same architecture diagram that describes every Kafka system you're ever going to build. You've got producers that write data into the cluster. You've got that cluster, you know a little bit more about partitions and replication and things like that now. And then you've got consumers, those programs that read data out. Every system you're ever going to build conforms to this diagram. And with that, you should have a pretty solid mental model of how Kafka works. A little bit about producers, consumers, brokers, zookeeper, partitioning, replication. All of these things put you on a solid footing to explore what's next. Hi, I'm Tim Berglund with Confluent. In this episode of the Fundamentals of Apache Kafka, we're going to dive a little bit deeper into how Kafka works. When we're done, you should be able to think a little bit more deeply about the actual code in a producer and a consumer, how those work. You should know a little something about exactly once semantics. You could talk about the way high availability and durability are accomplished in a Kafka cluster. And you can talk at a high level about how you might secure a Kafka cluster. Here is a minimal producer in Java. Now you'll notice this is just a public static void main method. So very, very simple standalone application. There are kind of 4 sections there that are boxed off. Let me talk about those. The first one is configuration. You make a properties object and you give it some configuration. Minimally, you have to tell it kind of like where the cluster is. That's that Bootstrap server list there. There's just a list of one address. That's a broker or a list of a small number of brokers in the cluster. So the client has some idea where to connect to and get cluster metadata from. You also have to tell the client the type of the key and the value. In this case, they're both strings, but it has to know how to take your language types, whatever those objects are in your language of choice, and serialize them into the bytes that it's going to send across the wire to the Kafka cluster. And that's what those serializer configurations are there. Next, you create the producer itself. In the case of the Java library, that's a class called Kafka Producer. And you'll note by the time we're done here, there are only 2 classes in the API that you absolutely need to touch. Kafka Producer is one of those. You pass the config to it and it starts up, and boy, there's lots of stuff happening in there, connection pooling and buffering and all kinds of machinery that ideally you'll never need to touch. It's just in that producer for you. Next, we add some shutdown behavior. Now, again, this particular application, when it shuts down, the whole JVM is going to get torn down. So it's kind of hard to have concerns about resource leaks, but this is just good hygiene. Make sure when we're shutting down, close down the producer. Finally, we actually send the data, and you see the key and the value that we're creating there. They're called key and value followed by a number. Yes, folks, we do write these ourselves. And the other class that you care about besides Kafka Producer is producer record. And you see that there. It's also a generic class, just like Kafka Producer is. You have to give it the types of the key and the value, which in this case are both strings. And to create a producer record, you pass it the key and the value and the topic you want to write to. So that's kind of the primitive of producing. It's key, value, and topic. Go to the cluster with that send method. We'll dig in a little bit later. What really happens when you call send? You're probably thinking, okay, it's off to the cluster and we're done. There's a little bit more to the story than that. But in a simple producer like this, you really can just call send and things will get sent. Now let's look at a consumer, but go for a different language just to mix things up a little bit. This is C#. And again, we've got a standalone program. So this is just going to run and consume and then shut down. But let's look at the 5 parts that we've got broken down here. First, again, at the top is configuration. That looks a lot like producer configuration. You have to tell the client where the cluster is. And you notice there's no types here. We'll get to serializers or actually deserializers in just a minute, but a little bit more consumer configuration in that configuration map. Next up in the C# driver, we set up some event handlers. So rather than getting messages back and iterating over them in an imperative way, we say, well, when a message happens, that on message event, take this action. And you see that genius consumer we've got there. We're logging it to standard out, which actually, I joke, but your first consumer that you write, you're probably going to do that same thing. That's super easy to do. You know it's going to work. It's comforting. You get feedback. So this is actually a great way to get started. There's also an on error and an on consume error handler set up there for various error conditions. But that's the way the C# driver works. You set up those event handlers so that later on, when we get to actually consuming, those will just run by themselves. But before we get there, we have to call subscribe. And this is a key part of pretty much any consumer language binding. You have to tell the consumer what topic or topics you want to be listening to. And here we just provide one. You can provide a collection of them. You can provide a regular expression that will cause you to subscribe to all matching topics if you just want to watch the world burn. That's up to you. You can do that. But the point here about consumers is that you can subscribe to one or many topics. If you've got lots of topics that have the same format of message in them, you may want to consume them all at once, and that is perfectly valid. Finally, at the bottom here, you have a while true loop. So that's an infinite loop. It's going to run forever. We're going to poll, and that's all that happens there. We say, hey, consumer, go check to see if there are messages. And if there are, what's going to happen? Well, our event handlers are going to run up above. So we'll be logging those messages to standard out when the on message handler runs. So that never stops. And this is typical for a consumer. This is how event streaming software, event-driven software works. When you're reading, you read forever. There's never a last event. You're never done. You just process each one and then wait for the next one. That's very, very typical. Can be a little disquieting if you're used to, say, web programming with the Spring framework. You're normally annotating methods, and those methods get called and they run to completion and they're done. And that's sort of comforting, and you feel like that's the right thing to do. But in consumers, you generally do just loop forever and always keep consuming messages. Okay, let's leave the world of the producer and the consumer and look inside a cluster. Now, here is a Kafka cluster with 4 brokers, and I want to talk about partition leadership here. So 4 brokers, we're looking at one topic. Now, probably this cluster has other topics, right? Probably not just a one topic cluster, but we're not looking at any of those. We're just looking at this topic called, somewhat prosaically, topic 1. To make the diagram look nice, we've made topic 1 have 4 partitions, which is the same number as the number of brokers, because man, that's beautiful. I point that out so that you know there is no required relationship between those two things. Okay, I could have a topic with 200 partitions and 4 brokers. I could have a topic with 1 partition and 4 brokers or 10 brokers or anything. There's just no correlation between those numbers at all. The slide looks nice in this way. It's easy to kind of see what's going on, but I don't want you to think that those numbers are in any way tied. Okay, look at the top there. That's partition 1 of topic 1. This topic has 4 partitions. Partition 1 has a total of 3 replicas. It has 1 on broker 1, 1 on broker 2, 1 on broker 3. And you probably see that the shading of partition 1 on broker 1 is a little darker. That's a darker color than 2 or 3. That's because partition 1 on broker 1 is the lead partition. Broker 1 has the leader for that partition. Broker 2 and broker 3 are followers, and they behave differently. So if you're a leader, that means you're telling producers and consumers that when someone wants to write to this partition, that producer should actually write to you, should send you the message, and you'll take it and you'll stick it in your partition log because you're the leader. Those writes happen to you. And when you're reading, when you're consuming, that consuming is going to come from you as well. Now, in versions of Apache Kafka after, I want to say 2.5, it is actually possible to read from followers and not just the leader. And there are some very important scenarios, usually in like multi-data center or multi-availability zone cloud deployments, where that enables some kind of cool functionality. But for the first order approximation, for you just wrapping your mind around fundamentals, you can for now think when a producer produces, it produces to the leader. When it consumes from the leader. So that leader is very important. And those followers are just trying to keep up with that leader. When new messages arrive at the leader, the followers will see them and write them to their own logs. So you see each partition has its own leader on a separate broker. That's really cool. What happens when a broker dies, like broker 4 goes away? Well, one of the followers of partition 4, in this case broker 2, will be elected as the new leader. And that's the thing the cluster does automatically. You don't have to think about that. When a broker dies, you might see a timeout in a producer consume. That's always possible. But that failover is going to happen. We'll have the new leader elected right away, and writing and reading can continue with no loss of data. That's how leader election works in Kafka. Now, when events happen, they can't really unhappen. You can't change the way they happen. Events are immutable. So the things you write into a Kafka topic, those events, those messages, they're immutable. They stay there. You don't get to edit them. But you might not want to keep them forever. By default, they're retained for 1 week. That's out of the box. Download Apache Kafka, install it, create a topic. It's going to have a retention period of 7 days. That is completely configurable globally in the cluster or per topic. Okay, it can be a very short period of time. I recently ran a test with a topic that had a retention period of 15 minutes, and that actually seemed like a good idea. You can set it to infinity. You can never delete data so that it stays in the topic forever if you've got the space for that. This is not really a technical constraint. It's more of a resource constraint and sometimes a regulatory one. This will be a business decision where the legal department might tell you that you have to retain this for 3 years, or you must not retain this for longer than 7, or I don't know, seems like 30 days is kind of a lot. That's a thing where the business weighs in. And it's, of course, an engineering decision too, because you're trading off cost versus various kinds of functionality you might realize by longer retention periods. I should mention, if all of this talk of immutable data and things never going away until some long period of time, if that scares you from a compliance perspective with things like GDPR, please don't worry. Those are beyond our scope here, but of course there are tools and techniques for handling that. People who have to comply with GDPR keep customer data in Kafka. That's absolutely a thing that happens. Again, beyond our scope, but I just don't want you to worry about it. Also, a brief note, remember we talked about those segments before, how each partition is composed of segments? Well, that's how data is actually expired. When the newest record in a segment is older than the retention period, then we can kick that segment out. We can delete that segment. So those whole segments stand or fall on their own. They get expired and fall off the edge of the world as they age past the retention period. Let's zoom into a producer and see what's going on inside there. I mean, you create a producer record and you call send and you think everything's fine and it's done. And honestly, probably everything is fine. But you might want to know a little bit more about what's going on. When you call send, that message goes through serialization. So you've had to configure those serializers. You've had to tell the producer library what the type of the key and the value are. And then that class is going to know how to take that object and turn it into the bytes that it passes on to the partitioner. That partitioner is going to see if there's a key, and if that key is not null, then it'll hash it and use that to determine what partition in the topic that will be written to. Of course, there could be a custom partitioner that's implementing some other logic. That partitioner will know that. That will be the custom partitioner then. That'll do that other thing. But generally, we're just hashing the key, and that sends it on to a partition. That partition is really like a little buffer where those messages get buffered up for a little bit before they get sent across the network. And the trade-off between how much batching we do in the consumer, that is how much buffering we do, how often we flush that buffer. That is the classical trade-off between throughput and latency that always exists in network interfaces like this. There's nothing particularly Kafka specific about it, but it's all tunable. That's all stuff that you can look into in detail when you're tuning your producers. The producer is also potentially waiting for acknowledgement when it sends a message. This is a configurable thing. And so it's a thing that you set a configuration parameter and the producer library just does it for you. But there are really three settings. One is no ACKs at all. That is, send it and don't wait for it to get written. The network transfer across that TCP socket has been successful, but you don't know what happened inside the broker. Did it get written to disk? Is the disk full? Is the disk on fire? We don't know. Anything could be happening in that broker. All I know is I sent it. I'm not going to wait for an ACK. I'm moving on. So this will cause data loss occasionally. Some messages will get lost, but you'll have very low latency on the produce side. You could also wait for just the leader to acknowledge the message. That's that middle case there. So the producer sends the message to the leader, which it always does, and waits for that reader to write it to the disk and then send an acknowledgement. When it gets that acknowledgement, it says, okay, this has been written to a disk in the world. I feel pretty okay about this. I'm going to move on. Your other option is to wait for all acknowledgements. That means all replicas that are up. In this case, you see there are three of them. There's one leader and two followers. Those two followers have gotten around to asking for that new message, and they've written it to their own disks, and they've told the leader, hey, I have replicated this, and it's on disk. Everything is fine. And that leader is waiting for all of its in-sync replicas to respond. It says, okay, I've got them. This is now on 3 disks in the world. I'll tell the producer everything's fine. So more latency there, but also a lot more safety. You're not going to lose data that way. Those delivery guarantees correspond in name, although not comprehensively, to the basic at most, at least, exactly once paradigm. So look at the skittles coming into the gears there, the skittles on the left, those little circles with the numbers in them. And I hope they don't get ground up in the gears because, you know, Skittles taste good. It would be better to eat them. But as those events get processed by those gears in the middle there are 3 ways the processing can take place. They can be processed at most once. That means that some of them might get lost. We'll never duplicate them, but some of them might get lost. If it's very important not to do something twice and it's okay to miss some things, then you want at most once processing. At least once means we're going to make sure everything gets through. In the process of making sure everything gets through, we might accidentally double up sometimes. And there are valid reasons for why that happens. And so sometimes we're going to see duplicates like you see here. You see 1, 2, 2, 3, 4, 5, 6, 6. So it's at least once you're saying duplication is okay. So if the read process for those messages is idempotent, that means that reading and processing one time and reading and process many times are the same. So the second, third, fourth time that you process a duplicate, you're not hurting anything. That's an idempotent process. Think of it like turning on a light switch, right? You enter a room and you walk in, you can't, it's dark and you're kind of groping at the wall and you move your hand up the wall and you bump the switch up. The light is on now, right? What if you do that operation again and you bump the switch up again? Well, the light's still on. It's fine. That operation is idempotent of flicking that light switch on. And so that would be a good candidate for at least once processing. Now, exactly once processing means that you're not going to miss messages and you're not going to process duplicates. Let's talk about that a little bit. Now, Kafka has provided this since about the spring of 2017. That's Kafka 0.11. So it's been a while now. Now, you may bump into people, and maybe you're one of these people yourself, who think that this is impossible in distributed messaging. There's this robust computer science result called the atomic broadcast problem that proves that exactly once is impossible. Well, no. And what the atomic broadcast result says is that exactly once delivery in a distributed messaging system is actually impossible. And so messages may get delivered more than once, and there's nothing you can do about that except drop back to at most once, right? So if you're not at most once, if you don't want to miss messages, you might send a message twice. What this transaction API does, and by the way, at the API level, this is an enhancement to the producer and the consumer. It looks exactly like a database transaction API. You begin a transaction, you do your writes, you commit the transaction at the produce side. Same side at the read side, you begin, do your reads, commit. So it fundamentally is a transactional API. And what it does for you is give you a guarantee that you will only process every message one time. Yes, some of those messages may be delivered more than once, but there's this switch in the producer that causes it to produce idempotently. So we're able to detect those duplicates and some other things with another topic that helps keep a transaction log. The details are fascinating and frankly, pretty available online. If you want to Google, you'll find talks from some of the engineers who wrote this stuff that talk about how it works. But this is a way that you can get exactly once processing semantics from a distributed stream processing system. And doing this yourself with the producer and the consumer is not too hard. Again, it's not too crazy of a thing to get that done. But it gets even easier when you start looking at tools like KSQLDB and Kafka streams. Then it's just a configuration parameter that you switch on. Let's dive into consumer groups in a little more detail. We have here, again, the canonical Kafka architecture diagram emphasizing some other components. There are those two producers. Each producer is producing to its own topic, and each of those topics has 3 partitions. There's one consumer group with 2 instances of the same consumer. We're going to call those instance A and instance B. So that's the same image, the very same program, just deployed twice. Now, that consumer is consuming both topics, X and Y. It's consuming all the messages from both topics. Now, let's look at how the partitions are assigned. And this partition assignment, by the way, is done cooperatively between the consumer group and the cluster. They just do this automatically. You never think about it. You don't have to take any action to make this happen. So partition 0 and 1 of topic X, those go to consumer A. Partition 2 of topic X goes to consumer B. It's going to do its best to allocate these fairly for each topic. And since there are 3 partitions and 2 topics, somebody's going to have more than somebody else. And that's just kind of how it works. And unfortunately for poor consumer A, that's exactly how topic Y works out as well. Partition 0 and 1 get allocated to consumer instance A. Partition 2 gets allocated to consumer instance B. Now, what happens when the composition of the group changes? To make this a little easier, let's simplify things and go to just one topic with 4 partitions. Initially at the top here, we've got a state where the consumer group has 2 instances. And so each instance gets 2 partitions. You get partition 0 and 2 on instance A and 1 and 3 on instance B. If we add an instance, so we've scaled that consumer out elastically, just at runtime, we just added an instance. The cluster says, oh my, I have to reassign partitions here, and it does. And we see only consumer instance A gets 2 partitions. Instance B and C get 1 partition each. And that happens automatically. You don't have to do anything. If one of those instances fails, well, the partitions that it's responsible for, which in this case are 0 and 3, those get reallocated to the other instances. So at the bottom, we have a fair scenario again. Now, that might actually be trouble, right? That there's only 2 instances. That failure might be very bad. And it may be that we're not able to keep up now. The messages are coming too quickly, and the computational expense of each consume operation is too high, and we'd better get another instance deployed as quickly as possible. But Kafka does that reassignment for us, and we don't have to do that ourselves. Now, one thing the consumer API doesn't do is it doesn't migrate state. So we're not looking at the code and what's happening inside consumers, but typically most interesting consumers are stateful. So you're going to remember something about messages that have come before. Maybe you're grouping in a window, and over the last 5 minutes, grouping up a bunch of values and running some reducing function over them, like an average or something. Well, that's all stateful. You have to remember things. And that state that had been in instance A when it died, it didn't go anywhere, right? Unless we were doing something with that state, the consumer API didn't help us migrate it. So this is a thing that Kafka streams and KSQLDB do for us. They do all that, frankly, fairly thorny state management, all internal to the API or internal to the KSQLDB server, which is a great thing. We'll cover those more later. I just want to point out that state is a thing that you'll have to think about here if you're counting on elasticity and fault tolerance in the consumer API. Now let's dive in now to compacted topics. This is a thing that's configured at the topic level. That topic on the top, let's just kind of look at that. It's got offsets, 0, 1, 2, 3, 4, those individual offsets, right? And keys and values. Now, if you just let your eyes go along the value, you have V1, V2, V3, V4, 5, 6, 7, 8, 9, 10. Those are all unique up to 17, right? Unique values. But there's only 4 keys. K1, 2, 3, 1, 2, 3, 3, 3, 1, 4, 2, 3, 4, 4, 2, 3. There's 4 keys that are unique. Now, if this is event data, like I always like to talk about my smart thermostat network, phoning home every minute, reporting temperature and humidity data and metadata about the household power supply and whatever else it wants to talk about in those values, those keys could be the unique IDs of those devices. So I've got a smart thermostat in my hallway, and that has a unique ID. And every time it phones home, that event gets stored with that key in the log. I might want to keep all those events, right? That might be useful to me to keep that whole history. So I'd want that regular kind of log. If on the other hand, I wanted to log changes to my user profile, I log into my smart thermostat network and I'm going to change my middle name and my profile picture and my zip code. Well, if I'm storing that kind of thing in a log, and K1, K2, K3, K4, those are not device IDs, but user IDs, well, I may not care about previous states of my user profile. I just want the current state. And that's why I use a compacted topic. So a compacted topic does what it sounds like. It takes all those keys and just takes the most recent version of each one. So if we turned that top log into a compacted topic, then you'd see K1 would have V10. It wouldn't have V5, wouldn't have V2, wouldn't have V1. Those are previous values of K1. K3 would have V17. It wouldn't be 9, it wouldn't be 8, it wouldn't be 4, just the most recent one. So that's a very important thing that you can do with the topic. If the topic is storing really entity data and you're really only interested in the most recent state of that data and not previous values, you can save lots of storage by making that topic a compacted topic. How do you troubleshoot a Kafka cluster? Well, great question. The classical answer is, of course, log files. This is a distributed system. Each node is going to have a few of its own log files. You can look through those. You can set up centralized logging and get that all in one place if you want. Of course, all those tools are available the way they normally are. There's also Confluent Control Center, which is a commercial offering, a part of Confluent Platform, that gives you at-a-glance insight into what's going on into the cluster and really is kind of the purpose-built Kafka cluster Confluent platform optimized monitoring and management tool to give you insight into what's going on in your cluster and how you could best keep it healthy. Now let's talk about security, starting with encryption. Now, Kafka will encrypt any data in transit. So that's client to broker, broker to broker, broker to zookeeper. Those are basically your connections. And we can encrypt all of those with SSL, you managing keys in whatever way you like to manage keys. That is all fairly doable, and there are great examples on how to get that done. Also supports authentication and authorization. So in order to establish, hopefully, an encrypted connection from a client, you have to present a principal name and a password, and then that principal name has to be authorized to do the thing that you're trying to do. And the cluster itself manages those access control lists to map principles to capabilities. There is not encryption in data at rest. So data stored in partitions in those log segments of partitions. Out of the box, that's not a thing. And so people do one of two things. One is they deploy full disk encryption systems so that everything on the disk is encrypted. And the other solution is to do that at the application level. Typically what will happen there is that you'll write a wrapper around the producer and the consumer libraries that does that encryption and handles the key management and all of that stuff. You're going to have various enterprise standards for how you want to do that. So that'll get done at the client level. So before the data even gets to the wire, before it can possibly get to a topic or a partition or a segment, it will already be encrypted. So that should give you a little bit of a better idea of how Kafka works in detail. We've drilled down into brokers and looked at how replication works and leader election, taking a look at what's going on inside producers, how consumer groups work, some really important things there, and giving you a rough idea on how Kafka thinks about security. If you're interested in some further reading on any of these topics, here are some links you're welcome to pursue. It's always good to dig into this stuff in more detail as you're interested. All of this, though, will prepare you to understand the parts of the ecosystem as we expand outside of broker and producer and consumer. what's in Kafka as a platform beyond those things. We'll look at those next. Hi, I'm Tim Berglund with Confluent. Let's talk now about how to integrate Kafka into your environment and some of the other elements of Kafka as a platform beyond just the fundamentals. Now, when you're done with this module, here's what I want you to be able to do. You should be able to explain how the Confluent REST proxy works, talk about the Confluent schema registry and why it's an essential part of a streaming platform centered around Kafka, sketch out kind of how and where Kafka Connect gets used and really what it's for, and also talk about main features of Kafka Streams and the goals of KSQLDB. I want you to have a good picture. And all these things together, these really fill out Kafka, not just as a distributed log with this produce and consume thing, but really a whole event streaming platform. Now, you could, by writing your own producers and consumers, integrate Kafka with any system in the world. If you know how to read data from something, a relational database, a mainframe, an S3 bucket, whatever, you could do that interfacing and then produce those records into Kafka. Likewise, if you know how to write to something, Elasticsearch, Cassandra, even HDFS, if you want, you could subscribe to a topic, consume from that topic, and write those messages out to that sink. You could do that, but you shouldn't because it's already been done. That's what Kafka Connect is. It's a distributed, fault-tolerant, pluggable, declarative data integration framework to get data into Kafka and out of Kafka, to integrate Kafka with legacy systems and external systems that aren't Kafka. Connect is its own infrastructure. It runs on its own server, its own instance, even like a cluster of Connect servers. And that's those Connect API boxes you see there. That's Connect running a server process external to the Kafka cluster. So on the source side, it's reading from some external system, producing into the cluster. And on the sink side, it's consuming from some Kafka topic and then writing into that external system. One of the most important things about Connect is the library of connectors. If you just look at these logos for these systems, you've got S3 and Elasticsearch and JDBC databases and InfluxDB and Salesforce and all these things. You don't want to write that data integration code yourself. If it's been written once somewhere in the world in a way that's reusable by you, you want to use that thing. Because adding that code or creating that code yourself, writing those connectors yourself, if they already exist, doesn't create any unique and differentiated value for you and for your customers and for your organization. You always want to take that kind of thing when you can. So there's this extensive library of literally hundreds of connectors that exist in the world. They're pluggable into Connect, and then you give it a little bit of declarative configuration information. That connector is off and running, doing its integration thing. Very, very powerful. Connect is a distributed system. You see here there are N workers in this Connect cluster. That could be 3, that could be 5, it could be 1. Those are all valid values of N for that Connect cluster. And each Connect worker runs one or more tasks. Each task is running a piece of a connector. If you can see the yellow boxes in each worker, connector A, task 1, connector A, task 2, connector A, task 3. So that's a connector that's able to be partitioned into 3 pieces. If you could imagine a sink connector that's consuming from a topic and let's say writing to Elasticsearch, if that topic has 3 partitions or more than 3 partitions, then those partitions can be assigned to those tasks. And Connect is able to parallelize the work of reading from that topic and writing into Elasticsearch. Those other tasks, whatever they might be, these same connectors can be partitioned and split among multiple workers. Now, not every connector is able to be partitioned. So if, for example, I am a source connector reading from a single database table in a relational database, well, that's going to be a single thread proposition. So there'll be one worker that has one task that's running that connector. But in general, connectors can be parallelized, and the work of distributing those tasks among the workers is done automatically by Connect. And the failover, if one of those workers goes away, of course, those connectors need to have remembered where they were, whether they were reading from some outside source or writing to some outside sink. Keeping track of where they were is a thing that Connect does automatically and stores that in that that Kafka topic, that internal Kafka topic you see at the bottom of the slide, that current state is managed inside the cluster. So you've got scalability and fault tolerance in Connect through those mechanisms. The Confluent REST proxy is really just a REST wrapper around the producer and the consumer. Think of it that way. Now, whatever language you're using, you almost certainly have support, community support, if nothing else, for some Kafka library. But if you don't want to do that, if you want to use an HTTP interface, the REST proxy lets you do that. It's a way to produce messages into topics, subscribe to topics, and consume from them, all through a fairly simple RESTful interface. And it also exposes certain administrative capabilities over that same interface. Now, if you can imagine building something big with Kafka, you've got lots of topics with data in them and many producers and many consumers, and maybe you've got a few topics that really are elevated in importance, and you find that that's very valuable data that lots of consumers have emerged to process in different ways. Well, there's a problem lurking here, and that problem is schema evolution. Now, schema evolution is always difficult, even in the way we've traditionally built systems as large monolithic applications with a database at the center. Migrating the schema of that database is not easy. And certain tools and practices have emerged around schema migration in those legacy systems. And the Confluent Schema Registry is our answer to that in Kafka, because you want to be able to version producers and consumers independently. They're already decoupled. So you want to be able to maybe release a new version of a consumer before you've got the producer caught up to be producing that new data format. Or, you've updated the producer, but there are 15 consumers of that topic and you can't version them all at once. There's different teams responsible for them. You want some of them to be able to be on the old version and have that compatibility with that old data in the old version of the consumer. These are real problems, and we need to be able to solve them. That's what Schema Registry does. With the Schema Registry, you define the schema for messages that are going to be in a topic. You generally do that through some kind of IDL or interface description language. Like in the case of Avro serialized messages, you'll use AVSC. We'll take a look at some AVSC in a minute. But you have this definition, this really text file that defines the schema of that message. And typically the process will look like this. You'll have some automated task in your build that will turn that type description into a language type. Like it'll create a Java class with that schema, and then you can use that Java class as a domain object, and producers and consumers will really automatically know how to serialize and deserialize that in a way that keeps the Schema Registry aware of that schema. Also at build time, there are ways of saying, hey, look, I've got a new version of this schema. Is this going to work? So I can know if my new proposed schema is going to work, given my new schema compatibility settings that I've got configured for the topic of interest. So helps us with schema evolution. That's super important. Schema is always going to change. There's no getting around that. And helps us make runtime and build time assertions of schema compatibility. Just to give you a quick idea how it works. Schema Registry is, like Connect, a process that runs outside the cluster. There's a server or maybe a few instances in HA configuration being the Schema Registry. The actual schemas are going to be kept in, no big surprise, an internal topic in the Kafka cluster. And the producer and the consumer actually talk over the network to the Schema Registry. When it comes time to produce a message with a new schema that the producer hasn't seen before, it'll say, hey, Schema Registry, here's this schema. Is this compatible? Okay, good. I'll go on. It'll cache it locally, so it's not doing that network hop all the time, and go ahead and do the produce. Likewise, on the consume side, the consumer will get that message out. There'll be a little schema ID in there. And if the consumer's never seen that, it'll go ask the Schema Registry, hey, give me the full definition of this schema. And so then the consumer will be able to make assertions about whether that version of the message is going to be compatible with the version of the schema that the consumer currently has. So that's basically how that works at runtime. This lets you make runtime assertions at produce and consume time. Hey, when I'm writing this message, am I going to break consumers out there? When I'm reading this message in, that's maybe something I didn't expect. Is it going to break me as a consumer? I mentioned the IDL, the interface description language. This is the Avro version of such. This is AVSC, an Avro schema file. And you can see it's JSON. That's a fairly lightweight description of the type. And this will be a text file that in a lot of cases, a team will say, nope, this is the type and this is source controlled. This is checked in with the project. It's a part of the same repo. And now when I want to change this, This is a change I can negotiate with the team the way I negotiate any other code change through a pull request. So I can propose that change. The team can say, oh, wait, if you do that, it's going to break this thing, or no, that's fine, go ahead. And so schema evolution becomes a thing that we negotiate just like we negotiate any other code change. And of course, when I say schema evolution, I generally mean adding fields, removing fields, changing fields. I could add a field to an enum. I could say we're going to start tracking social security number, or we're going to merge first name and last name into name and remove a field, all that kind of thing. Those are all valid kinds of schema evolution. So we've got data into our Kafka cluster through Kafka Connect, and we're able to push data out from Kafka also into other systems. We've got schema registry to help us manage schema change. What about actually processing that data? Now, you could do anything in a consumer, right? I can just consume data and do whatever kind of processing I want, but that gets pretty difficult. There's a lot of fairly basic stream processing operations like aggregating over a time window that are actually really thorny to write yourself. Well, KSQLDB is a tool that does that. It is the streaming SQL database for Apache Kafka. So if you look at that query there, that looks a lot like regular SQL. There's a join, and looks like I'm filtering on something, and there's a pretty sensible join condition there, but there's a lot going on there. And if you were going to do all that yourself in a consumer, that would not be easy, but it is pretty easy to take in through KSQLDB. With KSQLDB, you can do stream processing without standing up any actual programs of your own. So no matter what language you want to use to write your producers and consumers, you're writing your stream processing in KSQL. There's a KSQLDB server or cluster of servers that are adjacent to your Kafka cluster, and you can use the REST API to propose those queries to the server, which then they'll run. They'll run there forever. That's what KSQL queries do. They never stop. They're always taking new messages in, doing their processing, and emitting new messages into some result topic. You could do that again through the REST interface. There's a CLI that's pretty handy to use. Confluent Control Center, of course, gives you a really nice KSQL interface. You can look at running queries, create new queries, look at the results of a query and kind of scroll through them. Pretty handy web UI there. But that's the basic idea. You get to leverage all the power of the built-in Kafka Streams API without having to write a Java program with Kafka Streams, or think about any programming language other than KSQL itself. And Kafka Streams, I should dive into that a little bit. Kafka Streams is part of Apache Kafka. It's a Java API. I might say it's a functional Java API. If I really wanted to be formal, I would say it's a fluent functional Java API for doing stream processing on data in Apache Kafka. So definitely, like I said, a Java APIs, you're writing a Java program, but a lot of very complex operations like grouping a stream by a key. There's a lot that goes on when I do that. That's a one-liner. Now, to be able to make that work in a scalable and fault-tolerant way, grouping is stateful. I've introduced this whole state management problem, but again, this is one method call in Kafka Streams. And if I were just trying to do this in the consumer by making my own hash map and collections inside the hash map, and you can kind of imagine how that might work, that's great. But replicating that state, restoring that state if a node fails, scaling that cluster out and moving one partition to the next consumer in the group, all that kind of stuff, there is a lot of framework I'd have to build to do that. That's all inside Kafka Streams, all in that one method call. The method is, let's say, called group by, and all that stuff just happens. It's really, really cool. Other things like joining a stream, taking a stream that we've built off of a compacted topic and turning that into a table, right? And then joining another stream to that table, looking up from some key field events in this topic that have a corresponding key field in this compacted topic over there. You can kind of get that picture in your head, but that's all a few lines of code in Kafka Streams where it would be not very easy to do that yourself. So all kinds of power there. Integrating with exactly once processing semantics, that's a configuration switch that you set, and away you go. As I said, scale. I could take a Kafka Streams application, deploy it to one node, scale it out to 10. All that stuff works, and I don't have to do a lot of work to make it happen. Teams that are building microservices in Java will often find themselves using Kafka Streams. It's a very, very good match. And of course, you can do any kind of general stream processing in Kafka Streams that you'd like as well, if you want to do that instead of use KSQLDB. Kafka Streams has a very important architectural opinion, which is that it's a library. Now, you've already got a Kafka cluster, okay? That's one distributed system. We'd like to kind of keep that contained. You've got your consumer group. It's maybe a little bit of a stretch to think of that as a distributed system, but it kind of is. It's this cluster of nodes that Kafka is helping you manage. You don't want to stand up another cluster to deploy your stream processing application to. You want that application to live with your application code. If you're already being a Java application, maybe it's a microservice implemented in Spring Boot and it's got some RESTful interface and exposing some data model out to the world and doing some kind of processing, and you need to add to that advanced stream processing. Well, that's a library. You just want to declare that dependency and code against the library and deploy that stream processing with your application. Now, of course, that stream processing is extra work. So if you had a consumer group of, say, 2 nodes that got the job done, and now you've added all the stream processing, and maybe you need 3, maybe you need 4 if you're doing something really aggressive with a lot of data, that's fine. You already know how to scale a consumer group. Kafka has a story for that. So this is another way in which Kafka is built out of Kafka. Kafka's stream processing API takes advantage of scale and distribution techniques that are already built in this case, to consumer groups. You could kind of think of these as 3 things along a continuum. Now, the producer and the consumer, those are like the assembly language of Kafka, right? You can literally do anything in those, but you have to literally do everything. So simple things in the producer and consumer API make all the sense in the world. Complex things, you probably don't want that. You want to move to something a little more opinionated, like Kafka Streams. But if you look at the kinds of primitives you get, filter, map, join, aggregate, that's what you want. You want those as one-liners. So you're doing a lot less work subject to the more present opinions of the Kafka Streams API. Likewise, you want to keep going down that continuum. You've got KSQL, where it's much more opinionated. It's a dialect of SQL, and you're going to do things that way, but so much easier to deploy, easier to think about the programs. The programs themselves tend to be much shorter. I've written a Kafka Streams application and then written the equivalent in KSQL, and it can easily be a factor of 5 or 10 lines shorter, maybe more, depending on how you do your line breaks. But KSQL is much simpler and much more opinionated. So you've got this continuum, and you get to choose where you live along that continuum for doing your stream processing. So with those things, Kafka Connect, Confluent Schema Registry, Confluent KSQL DB, and the Apache Kafka Streams API, you've got a good idea how to integrate Kafka into your environment and do real-time processing on the data that you've got in Kafka. Hi, I'm Tim Berglund with Confluent, and in showing you the fundamentals of Apache Kafka, now I'd like to tell you all about Confluent Platform. As you're making Kafka into the central nervous system of your organization, you're adopting event streaming as a paradigm, building more and more event-driven applications. Other needs arise. There are other things that you're going to need. You're going to need replication between on-prem and cloud, or between regions in cloud. You're going to need automatic balancing of data within a Kafka cluster. You're going to need enterprise-grade security. You're going to need management and monitoring. All these kinds of things are what Confluent Platform gives you. And as you, as an organization, as a developer, mature in your use of event streaming, you start at learning Kafka, then you go to production, and then you find some application that really works and you scale it. And then you start looking, well, there's these silos in the organization. This worked well for us. Another part of the organization does the same thing, and you get connectivity of that data through Kafka between silos. And then really the apotheosis of this is getting to a streaming first paradigm throughout the entire enterprise. As you move up that scale, Kafka is exactly where you need to start. Kafka is the center of this system all along, but you're going to need more, and Confluent Platform helps you complete that journey. And just as Kafka is adopted across all kinds of verticals, so is Confluent Platform. You've got banking, financial services, retail, healthcare, travel, telecom, automotive, transportation, all kinds of industries have these same needs when they go to production and mature with their use of Kafka. Confluent Platform really adds a lot of value in those cases. And let's just look sort of at a layered diagram of what's in the platform. We have, of course, Apache Kafka as the foundation. That's that bottom there. And then you've got Kafka Connect connectors in that next layer labeled development and connectivity. There are a number of connectors that come with Confluent Platform that aren't available outside of Confluent Platform. KSQL DB is, of course, available for free. You don't need to be a Confluent Platform subscriber to use that, but proper platform support for KSQL DB is there as well. And then enterprise operations. You've got Confluent Replicator for operating clusters between data centers or between cloud regions. Auto Data Balancer to keep partition data balanced between brokers. And the Kubernetes operator, which is an absolutely huge thing. If you want to run your own deployment, you don't want to run in Confluent Cloud, you want to run Confluent Platform, but you want to run in Kubernetes, we've got a custom operator that makes all these elements of the platform run natively and properly in Kubernetes without you having to build all that functionality yourself. And of course, you've got management monitoring through Control Center and enterprise-grade security as well. And mind you, Confluent Platform is not particularly opinionated whether you run it in a public cloud or on your own infrastructure. Some of us kind of have this cloud first conceit where we think, well, everything's in the cloud. How could I possibly deploy a data center on my own? But there's some organizations for real, either financial or regulatory or data sovereignty reasons, do have to operate their own infrastructure. And in those cases, running Confluent Platform on machines in your own data center is a first-class thing to do. If you also want to run it in public cloud or exclusively in public cloud, that works fine. You could have a cluster in the cloud, a cluster in your data center, keeping those up to date through Replicator. That is all supported activity with great examples online of how to get that done. Of course, apart from all that talk of you deploying the platform, whether on instances in the cloud or hardware of your own, is one thing. The other major way to get this done is Confluent Cloud. Confluent Cloud is a fully managed Kafka service with, at the time of this recording, many of the elements of Confluent Platform available themselves as fully managed services in Confluent Cloud. And of course, it's available on the main public clouds, Amazon, Google, and Azure. When you create a new cluster in Confluent Cloud, you identify the cloud provider you want to host that cluster, and everything is taken care of for you. Confluent Control Center is a very important user interface that's a part of Confluent Platform. It is the web-based management and monitoring tool for Confluent Platform. Really a purpose-built system to show you what's going on in your cluster, and not just what's going on in Kafka, but all of the other elements of the platform as well. So what are your KSQL DB applications doing? What are your connectors doing? Is there something with MQTT proxy? All these things, we can visualize what's happening and configure them through Control Center. Confluent CLI is just what it sounds like. It's a command line tool that allows you to manage your Confluent Platform or Confluent Cloud deployment. And there are some things at the time of this recording that you need to use the CLI for, like RBAC, role-based access control. Configuring that is a thing that's done through the CLI. And many of us, we just kind of prefer this. So it's nice that this is here as a tool to supplement Control Center. So we can script things, we can do things in the terminal, where some of us are just more comfortable. I mentioned RBAC, role-based access control. This is a new set of security features that's been around in Confluent Platform for a little while, as of 5.3, which was in kind of the middle of 2019 as a preview. And what this basically does is, if you've got a large organization with a large number of principals, say there's different applications who are going to authenticate themselves to the Kafka cluster and say, I'm application XYZ, and I should have the ability to read these 5 topics and write these 2 topics. And that's all I should see, right? And then application ABC needs to be able to read this one topic and write this other topic, and that's like all that it can do. Well, if there's a lot of ABCs and XYZs in your world, if that gets up into the dozens, then those get difficult to manage one by one, to have access control lists for all the individual principals. Probably they fall into groups, right? There are what we call roles that those applications can take. There's probably a smaller number of roles that we group those many individual users, kind of virtual users, application names, but we group those users into those roles and then assign privileges to roles. And so those applications can authenticate themselves as a role. And based on that role, they'll get access to what they should have access to. So really just a way of grouping things together and managing security on the basis of those group names rather than on all the individual things. So it's supported across the platform: KSQL, Connect, Schema Registry, Kafka itself, all those things you have role-based access control to. Whatever it is you can authorize in each one of those components, you can do it through a role. I mentioned the Confluent operator a moment ago. If you are deploying Confluent Platform in Kubernetes, as an increasing number of people are doing, if you're not using cloud, you are more and more likely to be running in Kubernetes. And this is absolutely essential. There are other Kafka operators out available in the world, but the Confluent operator is one that is an outstanding Kafka operator and also supports all the other elements of the Confluent platform. So if you want to have a one KSQL DB cluster of 3 nodes and another of 5 and have Kubernetes manage those, well, the Confluent operator will help you do that. If you've got Kafka Connect and you want to manage that, of course, we're there for you. And of course, Confluent operator supports all the other components of the platform, whether you're running in the cloud or on-prem, doesn't matter. You can use Kubernetes and Confluent Platform together. One of the big things that this does is manage persistent volumes, since all these services are stateful, right? Particularly Kafka brokers are stateful, and KSQL DB servers are stateful. So managing those persistent volumes is a big thing. If you know a little bit about Kubernetes, that's not trivial out of the box. And so Operator gets that done for you. Also supports security integration, automatic rolling upgrades, automatic rolling updates of configuration, elastic scaling of Kafka, and other CP components. So all the stuff that you'd expect Kubernetes to do, it now does. Confluent Platform also includes a large number of supported connectors. Now, as I've said, there's hundreds of connectors out there in the world, many of them on GitHub and available as open source things, which is of course beautiful. But sometimes if there's a connector you find for kind of a more unusual data source, right? Maybe there's not a gigantic community around that, but you need it. And like the last commit was 2.5 years ago, and it doesn't seem to be very busy. I mean, there's open source. Years ago in open source, we used to talk about the distinction between free as in beer and free as in speech. Sometimes some of these connectors are free as in puppy, right? Like you don't have to pay for it, but you're going to give it a lot of care and feeding when it comes home. So the broader connector ecosystem in Confluent Platform is a good thing. These are developed by Confluent, supported by Confluent, and they should cover a lot of your bases. Once you get to 100 or so connectors, you've really covered a substantial proportion of the kinds of integration tasks that you might encounter, and you're doing it in a supported way. Those connectors and others, by the way, are available on Confluent Hub. That's hub.confluent.io. This is our curated set of all the connectors that we know about and can bring ourselves to put on the website. These are not all open source and they're not all commercial. License is specified for each one. So, you'll be able to see if this is like some completely Apache or MIT licensed thing, or is it Confluent community licensed, or is it a proprietary Oracle connector, or whatever. They're all there. And this is a handy way to search for them and be able to download them and install them into Connect. So with that, you've got a good overview of Confluent Platform. And really, you should think of Confluent Platform as an essential part of driving Kafka into the business. You could adopt Kafka as an open source thing. You could build streaming applications on top of it. You could use KSQL DB and Schema Registry in their free versions, and you could do all that. But once money is on the table and this becomes a strategic part of the business, often the business wants, as they move up that maturity model, a supported and official thing with the kinds of features that emerge as these applications become more business critical. You find those in Confluent Platform. So you'll probably find this useful as your adoption of Kafka moves up the scale. Hey, Tim here. Let's review what we've learned in this introduction to Apache Kafka. You're able to do a bunch of things now that you weren't just a little while ago. You know what a topic is, you know what a partition is, you know what a broker is, you know how a producer works, how a consumer group works. You kind of have an idea of how a minimal Kafka cluster is set up. You know what Kafka Connect is. You know what KSQL is. You know a little bit about Kafka Streams, and you know something about Confluent Platform. So really, you're pretty well prepared for further study. And let me tell you what Confluent has to offer in terms of your further study. So we've got some other training courses. We've got Confluent Operations for Apache Kafka. That's if you're interested in operating your own cluster. Like, you're not going to use the cloud. You're either going to run it yourself, maybe in a cloud provider or on-prem, but you're going to be tuning those brokers and configuring them. That's the course for you. Confluent Developer Skills for building Apache Kafka. That's for building applications on Kafka, really a deep dive into how to do things with KSQL, a little bit more about streams, some of the finer points of tuning the producer and the consumer to really dive in there and prepare you to do well. Stream processing using KSQL DB and Apache Kafka streams. So that's a deeper dive into KSQL and Kafka streams. So Kafka streams is a Java API. You'll do a little bit of Java programming there. And of course, KSQL DB is just SQL with streams and tables. So there's lots more to understand there. Like I just said, streams and tables. You need to understand what a table is and what a stream is. And honestly, that takes a minute for that to click. So that course will help you a lot with that. Then you've got Confluent Advanced Skills for optimizing Apache Kafka, which is just what it sounds like if you really need to dive in and tune the knobs. That's that advanced level optimization course. And you don't just want to take the course, you want to have something to show for it. So we have a couple of certifications available. There's Confluent Certified Administrator for Apache Kafka. That's a 90-minute exam, proctored online, 24 hours a day, just $150. And this will demonstrate that you've got a solid understanding of Kafka and Confluent products. And you should probably have like 6 to 9 months of hands-on experience before you really execute on this. But confluent.io/certification will get you more information on that. And there's also Confluent Certified Developer for Apache Kafka, also 90 minutes, also available online, also $150. But rather than focusing on administrative things, this focuses on development. If you're going to be building things with Kafka as a developer, this will certify that you have those skills. So, hey, thanks for attending this course. I really appreciate you spending the time. If you have any feedback, that goes to training-admin@confluent.io. And most of all, I hope you get started building things with Kafka soon. And I hope I get to find out what you do build as soon as you do.